Hello, everyone. Thank you for joining our webinar on MLOps with Feature Store. We are Logical Clocks, the makers of Hopsworks, and today as our speaker, we have Jim Dowling, who is our CEO. And as I mentioned, the topic today will be MLOps with Feature Store. Just a few reminders that the webinar is being recorded and everyone will receive the slides and the presentation after. And if you have questions, feel free to use the Q&A button to ask your questions, so we can follow them and make sure we answer them all. And we're going to keep the questions as we go and to the end. So stay with us until the end. And I think that's it. I'll pass it on now for you, Jim.
Great, thanks. Thanks, Natalia. Just one point of order about the questions. Sometimes when people use chat, there's an option that says talk to panelists, I think all panelists. So if you want everyone to see it, there's an option that says all panelists and attendees, so that everybody can see it, so that we're not answering a question that other people don't know what it is. I'll start sharing my screen, and you can see that the option, I think, is up here in chat. If you go to chat, you can see it here. There's this option, all panelists and attendees. Okay, so welcome. I'm going to just start sharing my screen here. And the webinar will go for about 55 minutes, max an hour. And my name is Jim Dowling. I'm CEO of Logical Clocks. And it is June. Now, one thing that came out last month in May was this very interesting report by O'Reilly. And you probably heard a lot of the cliches that 87% of models never make it to production. And what they kind of, O'Reilly did a survey of the community, and they basically figured out that, yes, a lot of that is true. And here were the problems, the barriers that were identified in this survey by enterprises on getting their models to production. So if we go through them briefly, we can see that skilled people is always a challenge. We as a company do not believe that a product can replace skilled people. There's no magic button you can press to get your MLOps pipeline. Programming is most likely a requirement, and if you're paying your data scientists a lot of money, then expecting them to be able to program Python is not unreasonable. Lack of data or data quality issues is the number 2 issue identified at 18%. So it's quite similar to lack of people. Now, this is really the data problem in AI, and that's why many of you are here for the feature store aspect of what we'll talk about today. And then we've other ones such as identifying valid use cases, which is obviously always a challenge. And if you don't do it, your competitors will. Company culture doesn't recognize the need for AI. There will be, any new change will have resistance. Ali Ghodsi, who's CEO of Databricks, says that the operational AI market will be bigger than the data warehousing market within 10 years, which is a pretty bold claim to make. But I think there is a lot of excitement now that AI can revolutionize how we interact, how products in particular interact with individuals, and how we can increase both the productivity of people and reduce the costs of doing business. And I think another challenge that we will address today is technical infrastructure challenges. So you do need to have platforms. There are many open source platforms out there today, but you can't put AI in production without support for platforms. And we're not going to cover the other issues like, how do I efficiently tune hyperparameters, which is a really interesting area, but it's not a major concern for people who want to put AI in production today yet. All right, a little definition, because I have an academic background, although I'll be honest, I don't really like this definition. What is MLOps? It's a definition that's not complete, because it says it's an extension of DevOps. So you need to know what DevOps is to get started. And that's not great. So it's extending DevOps to include machine learning and data science as first-class citizens in the DevOps ecology. So it's not really a complete definition. So what I think is, and I tried to explain this to lay people, because we hear the term all the time. What is I want to put my model in production. Well, what is a productionized model? If you can explain it to someone, because a data scientist can take some data, train a model with that data, and then they have a model and they can make predictions with it. That's a productionized model, is it? Not? No, it's not. Because if I use the analogy of a bus, right? If I have a bus that takes me from point A to point B and leaves me there, yes, it's a great trip. I maybe enjoyed the day out, but how did I get home? And maybe what I need is actually a bus service, something that brings me from A to B predictably And there's a timetable, and there's drivers, and the bus needs maintenance, and the bus needs to be filled up with petrol or electricity. So a productionized model is not a thing in itself. It's a service. It's a prediction service. It makes predictions on unseen data, yes. But to get that model to become a prediction service, you need to put in a lot of infrastructure in place. You need to train the model. You need to test the model. You need to deploy the model, and you need to automate it. And that's really what MLOps is really about. Be able to automate a lot of these processes. I'm going to add some more things to it. We think also it should be scalable, because if you get increased traffic, you shouldn't have to go and redesign your system. It should be highly available. If you get a failure in some container or some network, it shouldn't cause the service and prediction service to go down. And if your model is going to be online and not just a batch model, you will need to integrate it with the feature store, because frankly, what we see today with applications is the applications are stateless. They have very little local state. But if you want to make a prediction service that uses the enterprise's state, the history of the interactions of your users with the enterprise, the context in which the predictions are being made, that's where you go to the feature store. The feature store knows, hey, you've been interacting with us this many times. This is what you like. These are the things that you've bought recently. Here's the current state of what people like. Here's the current things that are popular. All this information comes from the feature store to be used to build more robust and more rich feature vectors that we can make predictions with. I'll get into that in a little bit. Now, our company, Logic Talks, we built an open source product called Hopsworks. So, you know, I floated this analogy to people, and people were like, well, hang on, can we not do something with hops? So here's another analogy for what a production model is. It's not the beer. The beer is the model. The brewery is the production model. And you can kind of work your own way around that. And there's a little diagram to kind of get you through that. So the previous definition said built on this concept of DevOps. So I'll just briefly define DevOps from a commonly understood perspective. DevOps is where when you're developing code, you automate the testing, the compilation, the packaging, and the deployment of that software. And the software is just software. So typically all you need is a version control system like Git. Every time you make a change to the software, you want to test that software, make sure the changes work. You like to automate the execution of those tests. The software itself probably needs to be packaged up. It might need to be compiled. It might need to be deployed in a containerized environment. And maybe you want to actually push it all the way out to your users. So this is typically DevOps, or automating the build, testing, and deployment of software, just the code itself. So we typically only need to worry about these actions, the triggers that come from software. When we change code, we need to do this. In machine learning pipelines, we'll see that changes in data also will require us to trigger these automated steps in our pipeline. So let's start out and look at what the machine learning pipeline typically is. And this is how we typically break it down. We have enterprise data coming in at the left, and we have models running in production on the right. Now, those models may run online, meaning they're operational models running 24/7, or they may be used by batch applications that run periodically. They take a big amount of data, and they use the model to make predictions on that data, and then you store the predictions somewhere that some downstream service will use them. But this abstract diagram here covers both cases. We have data coming in, it needs to be featureized. We need to take the enterprise data, validate it, clean it up, turn it into or transform it into features. So we may be doing aggregations on the data. And this is where the feature store comes in. It's going to be a store for these pre-computed features that can be then used to train models, but also we see this line at the bottom to serve models. So there should be another line going in here to model serving, where we can basically say that the features that are pre-computed in this single feature engineering pipeline, or what we call a feature pipeline, those features can be used by the data scientists to train models. And also when models are being trained, we're going to have some more steps. We're going to have to validate the models. And then finally, we deploy the models to, if it's model serving infrastructure, because it's an online model, we need to deploy them there. And then when models are running in production, they need to be monitored. So these are the steps that we typically involve in taking our raw data, and then the programs which are not shown here, but there is code. There will be code involved here. We'll need to do the feature engineering with some code. We'll need to train models with code, but we can see it primarily to data flow. Raw data is coming in, and models are coming out that are going to be used to make this prediction service. Okay, I did see a chat. There's something in chat, but it kind of disappeared. Okay, if you have questions, just throw them out there, and we'll try and answer them. So why do we need MLOps? So firstly, the data is going to keep changing, and when you have data changing in the enterprise, you would like the features in the feature store also to be kept up to date and refreshed. We need to keep updating those features so that, firstly, the online models that are being used, they can use the freshest features to make the best predictions, but also the data scientists who have trained models, the code that's used to train those models, we can automate the retraining of those models as new data becomes available. So we'll constantly need to update training data, and we'll constantly need to update these online features for the model. There are many teams involved in this pipeline, so it's not going to be just data scientists. Maybe in a small organization, data scientists might do all of it, but in larger organizations, you'll have an analytics team, a data team responsible for the enterprise data, the data scientists responsible primarily for the model engineering, and then ML engineers for making sure that the models run in production. And then you'll need infrastructure support for this. So you'll need to be able to do your feature engineering. You'll need some way of running the code. So maybe it's going to be a Python program, maybe it's going to be a Spark program. You're going to have to train your model. Maybe it's going to be scikit-learn on CPUs, or maybe it's going to be PyTorch or TensorFlow on GPUs. And then finally, you'll need some way to serve your models, either a model registry if you have batch applications, or you'll need to have some model serving infrastructure for online models. All of this you can orchestrate, so we need to automate the whole process. So you'll need some orchestration framework, and then we'll need to support the versioning of code and data. So we'll get to all of these parts. So let's start by the people problem. So in our pipeline here, we've organized it from left to right. So the data is coming in on the left. We have data engineers who are primarily responsible for that data. Data scientists and data engineers primarily interact through the feature store. The data engineers ensure that the raw data can be brought into the feature store. They may do some feature engineering, but typically they'll configure a lot of the pipelines that pull data from the backend data systems into the feature store. Data scientists will create new features, they'll train models and test their models, and then the models will get passed on to the ML engineers who run these models in production. And then finally, you do need to govern all of this, and regulation of these end-to-end AI pipelines is coming. It's coming in the EU very soon. So architects can ensure that you have compliance and governance of the data and the code as it flows all the way through these pipelines. We have a question, so I'm just going to take it. How do we package our ML pipeline when we do distributed training? Basically, how do we version our data set as part of the pipeline packaging deployment? And this is getting in a bit later. So packaging is a different question. So what we do in our particular platform is we can support distributed training by running Keras or TensorFlow or PyTorch applications over many workers. And it becomes, in our platform, it's called a job, and those jobs can be orchestrated by Airflow. But we'll get into that a little bit later. Okay, so let's go through these different, we'll go through the four different roles here, actually, that we've identified: data engineers, data scientists, ML engineers, and architects. But we'll start by looking at the data dependencies. So the data dependencies are not as big as you would think. In our platform, we have three abstractions. We have feature groups. These are the sets of features that come in from the backend platform. We have training data sets, and then we have models. And what you can see in this diagram also is that you have some feature groups that are connected directly to the enterprise data out here. We'll call that ED. And then we have some that are what we call derived feature groups that are computed just from features that are in the feature store. So if we're to be very high level breakdown of responsibilities, often data engineers write the data that maybe interfaces with the data lake, the pipelines that pull data from the data lake or data warehouse or operational databases or Kafka. And then data scientists can take that data and compute new features. So they can write programs in our platform, in any platform, and to create new sets of features from the data in there. So maybe they're going to aggregate it, maybe they're going to transform it. Trained data sets are basically groups of features that you put together because you say, I want to use these features to train this model. So we have a representation in our feature store, an abstraction that represents the model. It's a trained data set. Typically, you have a one-to-one representation here. So you've got one, for each model, you have one trained data set. You don't have to. It's best practice. We consider it best practice because then we can do provenance. We're able to go from the model back to the trained data set and then back to the features in the feature store. But typically the training data set it's not going to be taken from the feature store, often it'll be read from disk, because when you train models in TensorFlow or PyTorch or in scikit-learn, the natural way of doing that is to read files from the file system. So CSV files for scikit-learn, TF record for TensorFlow, or NumPy files for PyTorch. And that's typically how we find most people use it. You can, of course, get a pandas data frame directly from the feature store and train your model. That's totally fine. But for larger data sets and for organizing this data in a kind of structured way, often having materialized these training data sets to disk, it could be to our file system or to a bucket in S3 or a container in Azure Blob Storage. Okay, so let's look at what our data engineers do. Well, we know what they do basically. They take the data from the databases, data lakes, the snowflakes of this world. They have a bunch of tools that they love. They tend to like Spark. Some of them like Python. Scala is very popular. DBT is popular now, and they have many databases that they work with. The type of feature engineering that's very popular is a lot of companies start out by using SQL. So maybe you do your feature engineering in your backend database. So one thing that we can do in our platform is we can take a table that you have in Snowflake or in Delta Lake or in Oracle, and we can mount it directly in the feature store. So if you already have pipelines with tables containing pre-made features, you can just directly mount them into the feature store. And those pipelines will typically use SQL to compute the features. Often what we see now is that many companies are moving towards programming languages like Python and Scala to do feature engineering, but because you basically have more power. There's more libraries, there's more complex features, there's embeddings, there's graphs, graph embeddings, word embeddings, sentence embeddings, with different types of aggregates that are easier to compute in different types of frameworks. And then we have things like real-time features, so streaming data coming in that we need to compute features on at very low latency. So these feature pipelines, the data engineers are writing them. They're going to run at different latencies. You need some sort of orchestration framework to ensure that they run at the correct cadence. And there are many different events that can cause them to trigger. It could be time. You can be time-based triggers, run it every hour, run it every day. It could be some upstream data appears, or it could be some code is pushed to Git that you want to recompute. You want to rerun your data pipeline. Excuse me. So our platform is very open. You can do this feature engineering in any Python, any Spark environment, including our own. You can use any orchestration tool you want to, Azure Data Factory, Airflow, you name it. I have a quick question. I was just trying to take it. It sounds like there's a Spark adapter, but is there a Dask adapter? So, I mean, in our particular platform, internally, we support Spark for distributed, for feature engineering, but we also support Python. Our platform doesn't support Dask internally, but given that Dask works with data frames, we can push pandas data frames directly to the feature store. So you won't get the benefits of Dask from that, but the benefits of Dask are, of course, parallelizing. But you can use pure Python. That's not a problem. And we have a question in chat, so it's better to use Q&A rather than chat. But thanks. Different types of support. Yeah, okay, we'll get to that. So if you're using a feature engineering framework, you can do any types of features you want from, if you're using pandas or Spark, or if you're using frameworks like feature tools. We're talking about programming these pipelines. So rather than just point and click, which has its roles and usages, we're talking about typically writing some SQL or writing some Python or Scala to compute these features. Now, the data scientists have a bunch of tools that they love for managing their experiments and for, running for training their models. So, frameworks like TensorFlow, PyTorch, scikit-learn, of course. And then there are many frameworks out there to manage your experiments. R1 can be used as well. And data scientists typically will have some code that they'll use to train their models. But now in this case, they'll take their data from the feature store. So if we're talking about MLOps for data scientists, it's slightly different. This is a new realm for them. They're mostly used to using Jupyter notebooks, maybe for training their models. And in the olden days, you'd hand that code to some ML engineer who productionize it. I'll do a demo later where we can take a notebook in Jupyter and we can orchestrate it and run it in an Airflow pipeline. So you can actually turn it into a fully automated, orchestrated training pipeline. So training pipelines is where you want to get to. Training pipelines can be automated because new code has appeared. The data scientist has changed how they want to train their models. They may be using a new embedding or something like that. Or it could be that new data has arrived. So we could have the feature store could have had a dump of new data in a feature group that's used to create the training data set. So we create the new training data set, and then that kicks off training of a new model, and then the validation of the model, of course, the then deployment of the model if everything is looking good. So I'll talk a little bit how we do Hoodie for version data in our platform. There are other systems out there, but at least with Hoodie, it kind of integrates nicely into the Python world where we can, from Airflow, we can have sensors to look for changes in commit IDs in Hoodie tables. And then finally, we have the ML engineers, and they have their tools for serving models. I would say it's less mature for monitoring. There are a bunch of frameworks out there like Fiddler and so on. And companies like Selden do support for that. But you know, they're basically going to use the feature store primarily to retrieve features to build feature vectors that will be sent to the models to make predictions. And then the feature store also is a place where we can get statistics on the features in the models. So if we go to a training data set, we can say, give me the descriptive statistics for all of the features. Show me the mean and standard deviation values of all the features. And then I can compare that with the live traffic that's coming in to the model. I can compute the distribution of feature values on the live model and compare it with the descriptive statistics for the training data set. So that was the training data that was used to train the model. We have a couple of questions. We'll get them quick, see if I can get them. Hi, how do you keep data versions, the model version, and feature versions for various experiments in sync? Well, we'll have a look at that as we get through it. And how's Airflow different from Kubeflow? Kubeflow is a full framework for machine learning. It's not an orchestration framework. So within Kubeflow, there is an orchestration framework called Argo. You can check it out. It's similar to Kubeflow, but it's similar to Airflow, but it only runs primarily on Kubeflow. Okay, so finally, the often forgotten group, and there's probably not many of them on the webinar tonight, but are architects who need to make sure that all of this working in all of these three teams are compliant, and that the data is governed from end to end. So, you know, many of you might have used MLflow and see that there's a button which says, you know, please move model from development to production, and then write a message saying this is good to go. And that might be your idea of governance, which is fine. I mean, that's the first step. We have to get there. But, you know, we can think about how the more mature space of data warehousing is dealing with governance. There are massive companies like Calibra, Elation, and Informatica who provide these compliance and metadata frameworks for ensuring that they know exactly what's happening at all stages in the data pipelines and how the data is being transformed. So that's kind of come to the feature store space. We already have early work that we're doing integrating with these platforms. And really what you need is support for custom metadata in your feature store, the ability to be able to tag the different assets and to be able to understand the provenance. So where different features come from, and also where training data comes from, and where the training data that's used to train the model comes from. Being able to navigate from a model to a trained data set to features and back again is key to understand how it's being used and governed. I have another quick question from Pepita. What are the key metrics you record to track change from training data? Does it change based on the problem at hand, regression, forecasting? So I think I'll get onto our abstractions. We have two abstractions. We have the feature groups, and they are in our model, they're actually mutable. They change over time. So new data comes in and we update the feature groups. In our particular abstractions, training data is something that's immutable that you create from it's from a snapshot of data in the feature stores, in the feature groups, and then you create this immutable training data set. So the training data itself doesn't change over time. But what we do is I'll show you in the demo, we do compute descriptive statistics, min, max, standard deviation, mean values of individual features, and also properties such as uniqueness of features, important for categorical variables, and distinctness, and a couple of entropy metrics as well. Okay, so we have one more? No, okay, that was great. Okay, so we've kind of gone through the four different roles. We have data engineers, data scientists, we have ML engineers, and now we have architects that we're bringing in as well. And if we put the whole thing end to end together, what we can see is that this is from a blog post that I wrote about a year ago, actually, at this stage now. And I think it's still pretty up to date about what the state of the art is. But we have our data engineers who are doing these feature pipelines. They're really working with data ops. It's not, the main difference is that we're going to do more data validation than you would typically do in a data pipeline. So you want to make sure that there's no nulls or empty values that will cause your models to bork out. But for them, it's familiar. You have code, you check your code into GitHub, you have these pipelines that are orchestrated by some orchestration framework, and you're updating these mutable tables that we in the feature store. So if we go on the data scientist, this is where we get into a slightly new world. We have many different competing visions for how data scientists should do their development. Many believe that they should write only with PyCharm or with Visual Studio or whatever it's called, Viz Code, I think. And that code, of course, should be version control, which everyone believes. And there is now good support for notebooks for version control code in notebooks, and even doing diffs. We have a plugin in our platform in Jupyter Notebooks for diffing changes that you've made, and it's very, very useful. But the second part is you can see this data link here, which is novel. So if we do have triggers from our data, such as new data arriving at a feature group, does that kick off a new training pipeline? Well, there's actually interesting cases here, because in our case, training data sets take features potentially from many other feature groups. So you might have a change in this feature group and have no change in this one. And you only want to create the new training data when there's changes in all three. So in fact, what we do typically in that case with customers is we use tags as a way to maintain state. So we can attach arbitrary tags, JSON objects, to these feature groups, and we can know when the last update happened. And when an update happens, we can add a new tag saying there's a new update. And that way you can easily reach agreement between all of the three feature groups that have been successfully updated. Okay, now I can go ahead and create my training data set. So your MLOps platform, or if you want to call it CI/CD platform, is really about, okay, I do my development, and now I want to automate the training process. So the typical steps are this, creation of training data, the training of the model, and then the validation of that model on many different slices of the data, and then the deployment of the model. And you can also validate the deployment as well. And then finally, when you get into monitoring, there's a number of other steps you can do in terms of, we already talked about data drift as one thing. So taking the training data statistics from some of the training data used to train the model and comparing it with computing also the descriptive statistics on the live traffic, and then comparing those to identify data drift. But data drift is just one thing. There are outliers. There's many other, there's also concept drift. There's a bunch of different problems that you need to deal with in live models that you're training. And we haven't even touched bias as an issue. Now, many of you will have seen this diagram, so I want to just bring it in because I don't agree with all of it. You can see here, there's no data engineering in this picture. The world starts at the feature store. And they've kind of divided it up into two phases: experimentation at the top, and then actual production at the bottom. And we'll see that we kind of have a much more fluid boundary, that we don't have this distinction in our platform that you need, that Google are advocating in this abstract diagram. Remember, this is abstract. It's not mapped to particular technologies, even in their case. But the basic idea for development is that you do some analysis in your data. Now, we'll see in the feature store, a lot of the EDA is already done for us. We can just look at statistics and data. We can preview data quickly. And then you do some basic experiments. You generate some code and you're happy with it. And then that code that you have, you need to package up into probably a Docker container that you can then submit into some pipeline. It could be Kubeflow pipelines or some other framework that will basically kick off all of these different steps that that are identified here. And you can see there's a couple more than the ones I mentioned. So data extraction and data validation, these happen before the feature store typically. At least data validation should happen before the feature store. So I would just cross this one out here and say, don't do it after the feature store. You can get in trouble. Data preparation, again, there are many transformations you will do after the feature store. So often the feature store will store strings and numerical features, so categorical numerical features in plain text format, and you'll do your one-hot encoding after it. You have choices here. So in our platform, we do have real-time feature transformations we can attach when we're creating training data sets. It's coming out in 2.3, it's not in 2.2 yet. But the other option is that many people do is that they use scikit-learn pre-processing pipelines or Keras pre-processing pipelines or PyTorch pre-processing pipelines, where you do your transformations and you save then the object, the pre-processing object, and then in your serving model, you read up that pre-processing object and you apply the same transformations in that pipeline in the serving layer, so that you ensure consistent feature engineering between this training pipeline and then the serving pipeline. But there's a couple of others here. So you can see then if we just follow along the track here, there's a model registry, which of course you'll need. And then this model is is deployed to serving infrastructure. And then the prediction service I mentioned before will go back and use our feature store, which is back here, to pull in the features to create the feature vectors to make the predictions. And then this all needs to be monitored. And there's a metadata store to store a lot of that. So that was kind of the abstract intro, and it took a good few minutes, and I think there were no more questions. Let's keep going. Hopsworks, you can try it out today. Hopsworks.ai, it's a managed platform. You get $4,000 of free credits. You can install it. There's a community version, which is fully functional, and then you can install it with one line in bash code if you have open internet access and you have a Ubuntu 18 or CentOS 7 machine. And then there's an enterprise version, but I won't say anything more about it. There's a link in there, I think, from Natalia passed in. So it's an open platform. Do your data engineering, data science, ML engineering, and compliance directly in any platform you want. You can also do it in our platform. And that's where we're kind of unique. We're not asking you to use a DSL that we define to do your feature engineering. We're assuming that you have some Python environment or some Spark environment. So it could be Scala, Java, or PySpark or SQL. And those environments, you can do your feature engineering to push the features into the feature store. And then you can use your own data science platform to do your training. And if you want to use our platform from all of us, great, So we have a quick question. I'll interrupt my flow of thought. What is design of your feature store? What database is used? Okay, I'll take it while we're here. Our feature store stores its data. If you're on the managed platform in AWS, the data will be stored for the offline feature store in S3 or in Azure Blob Storage. It's Parquet data with a layer of metadata called Hoodie. Hoodie is very similar to Delta Lake. And we can access it through Spark, or we can access it through Hive. So we actually do SQL queries through Hive in our platform, or we can Spark programs and access it. And then the online feature store, we have a database called RonDB. It's a fork of NDB cluster. The inventor of it works for us. His name is Mikael Ronström. And it's the world's fastest database. I'm not going to promote it or say much more about it, but we think it's really great. The only thing I will say is we've been up against competitors and we're about 150 times cheaper than them when you have relatively high loads on your feature store, the online feature store. Okay, so I'm going to just start very briefly. What is a feature? And I haven't said what a feature is. I haven't defined it. If you're a data engineer, it's your table, it's the columns, but we transform it. The numbers we're going to normalize within a range, maybe 0 to 1. The strings, ultimately, we're going to change from a string to a binary representation called one hot encoded. We'll aggregate a lot of data. If we have a lot of entries over a period of time, we might sum them all up to get to know what the average value of that was over that period of time. And this is the data then, the numerical data that we're ultimately going to feed to our models to train them. But also when we want to make predictions, it's the same data that we're going to use to make predictions. Now, our feature store and any feature store, it's designed to decouple these pipelines that create the features from the models. And the reason why we want to do that is because the pipelines can keep updating the features, and then you're free as a data scientist to go create as many models as you want. You do not need to write an end-to-end pipeline to get this model in production. So this is a beautiful thing, particularly when your feature store gets bigger and you have more and more features, you're free to go off and just join the features together and get your training data and train your models. So the other abstractions that we have apart from the feature itself is the group of features. It's just a table. Now there has to be a primary key when it's served online, and there can be multi-part primary key, not just one. There could be several primary keys. We have a customer with up to 8, which is unusual. And I talked about training data sets already. A training data set is if you wanted to train a model with features that are not in the same feature group. So they're in different tables. They're coming in at different cadences. So this one's being updated daily. This one's being updated every hour, but I want to join them together. So I pick the features, I say pull these together into the training data set, and the feature store is smart enough to have a query planner to find a common join key. You can override it yourself. I'll have a look at the code in a minute so you can see how this is represented in actual code. And then the final abstraction is the role that you give to your online infrastructure to make the prediction. Because what we'll see is that when you're using a feature store, your application will supply things like, hey, here's the user's ID, or here's the session ID, or here's the blank ID or the product ID. And with that ID, because that's the ID that comes from our feature group, we go and look up the features associated with the product or the user or the shopping cart. And with those features, so this primary key on the left, we can see here, we're going to go to the feature store and we're going to say, look up all the features regarding this ID, and we get back these N features. And of course, when we're making a prediction, we don't have the label. So the trained data set, of course, we're assuming supervised machine learning, but in this case, we don't have a label. So we're going to predict that. So the model itself is going to give us this prediction. And it could be regression or classification. So this is how we put them together. We have our raw data out here, the enterprise data. It gets turned into these features that belong in feature groups. We can create training data sets from the features in the feature groups, and then we train models with those trained data sets. And the models will have, and the trained data sets will have a lot of statistics with them that we can use for things like drift detection. Okay, and this example here, and I think we'll share the slides, and Ty will share the slides, is for the area of frauds. We're taking in financial transactions and user features, joining them on the user ID, and then we're creating fraud trained data set for that, and then a fraud classifier to classify whether this financial transaction is suspected of fraud or not. We actually have a really nice work-through example with 7 notebooks in our GitHub repo. If you're curious, just look for AML. In our GitHub repo, and you'll find it. So when we want to turn this into a proper MLOps platform, and with these abstractions, we actually decompose this end-to-end machine learning pipeline into 2 parts. We have the feature pipeline. This is the programs that will update all of the features in the different feature groups, and each feature group will typically come from its own source, and will be updated at its own cadence. And then we have the training pipelines that will take the features, create the trained data sets, and train the models and validate the models and deploy them. So when we say end-to-end, it's really not one end-to-end pipeline. It's the feature pipeline as its own set of pipelines, and then the training pipelines are a different set of pipelines. So if we think about how do we then, when do we run these pipelines? Well, typically what we do in the kind of DevOps and MLOps world is we say, well, what are the actions or the triggers that can cause these pipelines to run? And I mentioned already things like code being committed, new data arriving, time triggers happening, so daily or every hour. And there are many different orchestration platforms. So Airflow is extremely popular. There's GitHub Actions, Jenkins, there's Azure DevOps. There's a bunch of different frameworks out there that can use to orchestrate the execution of these pipelines. I'm going to show you Airflow, but the principles apply for any of them. In our particular platform, we have a Python API. So, we have customers who use Jenkins to kick off these pipelines, and it all depends on what you want to do. So let's have a quick look at some code. This is an example showing you how we write features to the feature store. So what we're doing is we're reading up data from a location on Azure Blob Storage as a data frame. This is a Spark program, a PySpark program. We do some feature engineering, and then we save this data frame. This is a DF object here. We save it to this thing called FG. It's a feature group. We talked about it already. What we'll notice is that we have a version number. This is the schema version. And this is very important again for production use, because when I write this pipeline and run this pipeline, if somebody decides that they'd like to evolve this schema, they'd like to maybe drop some columns, change the implementation of a column, maybe they have an embedding and they want a new implementation of the embedding, well, they'll need a new version of the schema, and it won't affect any existing pipelines that run with version number 1. They can go off and work with number 2. They'll need to backfill it, but then they're free to do whatever they want there. And knowing that version number 1 of this pipeline will continue to work properly. We can see also that what we have here is that we have a primary key. It's a multi-part primary key. And then this data is going to get written to both the online and offline feature stores. And we set online enabled to be true. Now, this is creating the feature group. If the feature group already exists, you can just get a reference to the feature group object and then insert your data frame with the new data that's going to come in. And by default, our feature groups are backed by a framework called Hoodie that I mentioned already. We'll have Delta Lake support soon. But every time you make an update in Hoodie, it's like a commit in GitHub. So you get a commit ID and you get a timestamp associated with it. So when we insert this new data frame, and it's not just insertions, it also does deletions and it also does updates. So we often call it an upsert rather than an insert. What will happen is we'll get a new commit. So what we're able to do also is to go back in time and say, I would like to know I would like to read this feature group as of this point in time. And you can get back a data frame as of that point in time. We can also get the changes that happen in an interval. And those changes we can get back as a data frame. So this is how we're going to do our data triggers for kicking off new pipelines. So when a new commit arrives, we can have Airflow have a sensor to basically listen for this event. Or what we can have as well is we can basically, in the feature engineering pipeline ourselves, we can also, if we want to, we can trigger a new event, a new workflow to run at the back end, if so desired. I think there was a question there, but it then disappeared, so I'll keep going. So what we can see here also in this diagram is that we can have multiple versions of feature groups. So there's two types of versioning happening here. We have the versioning at the schema level where we're adding, removing columns, and then the versioning at the data level, which is like Git, where every time we change the data, we get a new commit ID unique to identify the data as of that point in time. Now, as data flows into the system, we do have support for data validation in our platform. We build on a framework called DQ developed by AWS. So what you do is you can define what we call rules or expectations, and there's tons of rules, things like completeness. If you want to check if there's any missing features or null values, you can check minimum values of features, maximum, mean values, and you can look for things like feature drift. You can encode the rules. People often say, do you do feature drift? I say, well, tell me what feature drift is for your domain, because it's different for every domain. What you basically need to do is attach these rules to a feature group, and then every time you do an insert into the feature group, the rules get executed. And if you set an error and the rule doesn't pass, well, then there'll be no data inserted. And that's one of the nice things about Hoodie is that you won't have half of your data inserted and then the error happening and half your data in and not half your data out. It supports ACID insertions. That means atomic insertions. Either all of it's inserted or none of it. So in this case, nothing would be inserted if the error fails. And then you need to investigate the error, resolve it, and then rerun your pipelines. So in the UI, we have support for these expectations. You can see it here. They can see this history of expectations. We also support real-time feature engineering. So we have one customer that has data arriving at a Kafka topic, and 10 seconds later, they're using that data to make predictions. And the way we're doing it is we're using Spark Streaming. And this is just showing you kind of the API for it. We have this data frame reading data from Kafka. We deserialize that data frame, and then we build this 10-minute aggregation window computing the number of events that have happened in that 10-minute period of time. And then we can insert that data into this feature group. And then this can obviously insert to the online feature store if you just want it online, but you can also insert it to the offline using Hoodie as well. And there's notebooks for this if you go to docs.hopsworks.ai, there's notebooks for all of this. So it's called examples.hopsworks.ai. There's a link from there. So let's move then briefly on to training data set creation. So we have some support for joining these features together in a Python-like DSL, if you will. It's Python code. It's very pandas-like, so it's Pythonic. But basically what you do is you say, select the features from your feature group. Here we're selecting all of them, but you can of course select just a subset of them, a projection. And we're joining them all together. So the query planner will actually find that the common primary key here, that's the largest overlapping set of primary keys between these feature groups, is the location ID. And we get back this object here. We can get a pandas data frame from it and train a model. That's fine. But in this case, what we're doing is we're creating a training data set in the TF record file format, and this will get stored on disk. So you can store it to a bucket in S3, or a container Azure Blob Storage, or you can store it to our file system. And then the next stage you're going to do, you want to train your models. I'm not going to go into this because everyone who's a data scientist here will have seen this, but typically you're just going to read up the training data set that you created, in this case, in your bucket in S3, and you read up as a data set in TensorFlow. I didn't show in the previous example, we do have support for random splitting of data into training, test, and validation data sets. You just add those parameters, and then you can read up your training and test data sets as different data set objects in TensorFlow. We even have API support, so you can do it in a single command. Now, the other, I guess, part of which is not really as automated, I would say, as it could be, is model analysis. That's once you've trained your model, you want to validate it on different slices of the data. Our platform has a plugin called What If tool. It only works on classic Jupyter, not on Jupyter Lab yet. But we have support for both Jupyter Lab and Jupyter Notebook. And it's a great way of actually, slicing your data and then understanding the performance of your model on different slices of data. So you'll have some holdout data, and then visually you can then inspect it and do some inspections, and then you can write some code to encode those discoveries that you've made and automate those and run those as tests then. Now, I did mention Airflow a couple of times. We do support Airflow on our platform, and you can use Airflow to orchestrate Spark jobs or Docker containers or Python programs or even notebooks. And the notebooks can be Spark notebooks or PySpark notebooks or Python programs. But there are other ways to orchestrate these frameworks. And then finally, we do have model serving support in our platform. Kubeflow model serving is we just released in 2.2. And we had a talk at Spark Summit if you're interested about how we monitor these models in production using Spark to read from Kafka, because we store the prediction logs. The prediction requests can get logged to Kafka that runs on our platform, and then you can read those prediction requests and try and detect things that we talked already, like data drift and outliers. And then the really interesting part of that talk, if you want to just check it out, is we write back the data to the feature store, and we use the same data validation rules that we had earlier on in the feature engineering pipeline. We reuse them because we can just reuse them to write the data to a logging feature group. And if we're looking for data drift is with respect to the mean and standard deviation values of the features in the feature store already. So that's a really nice kind of insight there. This is a big diagram. I'm going to kind of skip over it, but basically this is the equivalent of the Google one. You have your data lake, your feature engineering, your model training, your model deploying, and we have this meta store. In our platform, ROMDB is our meta store. We've simplified the platform by having one database is possible to act as both the online feature store and the meta store for all of the metadata in the platform. So, if you have questions, just shout at me. I'm going to demo a bit. We have about 10 minutes left to do a demo. And I've taken a few questions already, but we can kind of just go through them. So this is Hopsworks.ai, and you can, like I said, if you register for an account, you'll actually get a demo cluster. You can kick the tires on it. And if you really want to get the best out of it, you connect it to your AWS account or to your Azure account. And you'll get $4,000 of free credits. There's a little bit of work to do. You have to create a cross-account role in AWS, and in Azure, you need to create a subscription ID and a tenant ID. But then you're able to create clusters. I'm going to just skip through these, and I'll open these clusters I have here. Just a couple of words before we do that. The clusters have a head node, and that's where the online feature store and other services like Kafka are running. And you can add and remove workers. You can remove them dynamically, so you only pay for usage. You can even configure auto-scaling, which is really useful for MLOps, because you can set up pipelines to say, okay, run this at 3 in the morning, and the workers will get added. And then when the job's finished, the workers get deallocated, and you only pay per use. So there's usage-based pricing here, very similar to Databricks, priced a little bit cheaper. So let's jump in here. There was a question there, but maybe someone answered it quickly because it says no open questions. It's in the chat. Okay. Sorry. Do you integrate with SageMaker pipelines? Yes, is the answer. Well, SageMaker pipelines are really just, they're Python, it's a bunch of Docker containers chained together. And we have Python APIs and you can call them from within SageMaker pipelines. So I didn't show some of the examples of how you connect. You basically have an API key that you get in the platform here to connect. So we have a new UI, which is feature store centric. I'll just show it briefly, but because I'm going to do Airflow, which isn't in the new UI yet, this is really the feature store. Everything feature store is here, including new stuff. You can see the storage connectors to connect to bunches of different backend data warehouses and data platforms. So everything from S3 to Azure Data Lake to Snowflake to Redshift and so on. But the main abstractions are these feature groups, and some of them, you can see this one is on demand. It comes in from an external database. Some of them are online, they're green. Some of them are black, they're just offline. And some of them, if we take like this one here, it's a Hoodie feature group. We can see things like expectations associated with them. And we can see the statistics that have been computed over them. So we can see things like the min, max, distinct count, and standard deviation of feature values. We can pre-compute correlation matrices. These are done for free. Like when you ingest the data, if you leave this turned on, the statistic computation, it will see all this. So we can see what happened. We can see a history of all events, because again, it's like the commit log from Hoodie. We can see when data was added, removed, validation was performed, and the results of those validations. And every time we ingest data, we'll compute new statistics, and you can go through those as well. And training data sets are very similar, except that they're in the file system, but the metadata is here. If you're interested in governance, there is support for tagging. We can define what are called schematized tags at the top level. Here you can create a schematized tags with the tags that you need, and they're typed, so you can have strings and booleans and so on, and you can attach them to your feature groups. So we can then search globally. I can search based on a free text search here, and I can find feature groups. We can find individual features, and we can go ahead and inspect some of these values and get a quick overview of what's in there. So this is the new feature store UI. What I'm going to do instead is I'm going to actually go back and I'm going to show you the pipeline that we discussed as a kind of an MLOps pipeline. I'm going to create a new project, call it webinar. And what I'm going to do is I'm going to upload some notebooks that I have, and I'm going to run those notebooks as two different pipelines. One is the Airflow pipeline, the feature engineering pipeline, where I'm going to insert data into the feature store. So that pipeline and those programs would typically interact with a backend database or a data lake or a Kafka or something like that. And then we'll do the training pipeline after. So a question from Gina: is there a good way to see all of the data for one primary key rather than by feature group? You may have shown it. I didn't show data. You can get data preview there. If you really want to get the data itself, well, there is a SQL API. So you can use SQL. You can do it from, if you like your notebooks, which many people do. There is support here for GitHub, you can see in GitLab. I'm going to skip them for the moment. I'm going to just start a Jupyter Notebook, and you can run from the UI. You can call fs feature store object.sql and then run your SQL. So if you know the primary key, you can see select star from this row. What I'm just going to do here is I'm just going to upload a bunch of notebooks that I got off Alex, who is here. So let me just upload these notebooks. No, I'm not going to create a folder. I can just upload them directly. Okay, these are the notebooks. Okay, so we've got 6 notebooks here, and they're in the file system. This is Jupyter Labs. It just kicked off. It's starting. So what I'm going to do is basically just show you a notebook, and then I'm going to run these create Airflow pipeline, create jobs from these notebooks, and then what we'll do is we'll basically look in here. So what we'll do is we can see our notebooks here. So what we'll do is we'll run those jobs inside an Airflow pipeline. So we can see how easy enough it is to get started. Now, I'll only set up time triggers for the moment, but you can easily set up other triggers outside of it. So let's have a look at this notebook just to see what it's doing. It's using our library called HSFS to interact with the feature store. If you're not running this in the platform, you'll need to supply an API key. But if you run the code in our platform, you just call connect, and you'll get back the connection object. And from there, you can get the feature store object. So if you do have you can have multiple feature stores in our platform. You can have a development, a prod, you can have a staging feature store, and each one can represent different objects. So typically, you would develop your features in a development feature store, and then you would migrate them to the staging feature store, and from there to the production. So we have role-based access control within these projects that I haven't really discussed yet, but basically what you would have is you have someone who's able to, only a certain group of users, a role called data owner, are allowed to add features to a given feature store. So you might have some people responsible for the features, and they're the only people who are allowed to add to the production feature store, and other people could develop them in their own private experiment project or in a shared one. And then from there, you can migrate them over. So let's have a quick look at this. We have a feature store object. We have it's creating some data. It's creating a feature group, and it's creating a Spark data frame, and it's just going to write that into the feature store. So it's a very simple program. Let's turn it into a job, and I'll answer the question in a second. So I'm just going to create a job from that particular, we'll call it number 1, from that particular notebook. This is the job, the feature engineering job now. So it's just a single notebook. It's not a pipeline as such, and it's a Spark job. So I'll select Spark Dynamic, which means it'll use as many workers and resources as we need. I can trigger this directly here in the UI, or I can actually set up a workflow in Airflow. So I'm going to set up a workflow in Airflow. Now we do have support for automating this, or sorry, for helping you write your Airflow programs, because a lot of data scientists don't like Airflow. Even though it's Python, it's a bit complex, and I understand that. You can define a scheduler interval here. So say run this daily or run this every hour. I'm just going to leave it as once for the moment. But what we have is support for adding a job. So I just created a job from a notebook, and I'm going to add that job here. And that's it. Wait for it to finish, yes. And now I've added one job to my workflow. So if you're familiar with Airflow, what this is a linear tag. It's a set of steps that we can run one after another. That's what I'm going to define. In this case, it's one step, so I get this one program here. Now I'm just going to answer the question before. Is there a good way to see all of the data for one? Oh yeah, we answered that one already. Yeah. Okay. Any more? There's a few others. Yeah, we have another one. So what's the idiomatic approach to use Hopsworks or some platforms for storing and managing data for CV, so computer vision models? So they usually have large artifacts, images, and they need to be stored in separate data stores, which use complications to maintain data consistency. So what we do in this case typically is that we've worked with self-driving car company with millions of images. We actually support, what we do is in the feature store, always store the paths to the files. So your feature group ends up being the path to the file and all the features that you're interested in. So it might be, for example, bounding boxes that you've identified around it. It might be segmentation information, and all that information is stored in the metadata. And what we're able to do as well in our platform in particular, which is very interesting, is we can add tags to these images. So you can have your image in the file system here, and you can have, in our particular platform, we can have millions or petabytes of data potentially. And we can attach this metadata, and then you can search for it up here. So you can basically search for images with certain bounding boxes because it's all being indexed on Elasticsearch. But typically, yes, you can store large binary objects, blobs in the feature store, but it's not typically best practice. Okay, let's go back to Airflow because I was there, and let's open Airflow. So this is the Airflow program that was created from the UI. We can see, I'm going to run out of time actually. I did promise we'd finish on time. So let's open open an Airflow. And did I call it workflow? I call it feature engineer, yeah. So that's another one that I created earlier, actually. So let's kick this off, the feature engineering one. It actually, when I turn it on, it will start running automatically. And we can go back and have a quick look at it. So it's going to start this job running here. So you can see our job is running, it's converting the notebook. And you can view this in Airflow in the graph view. You can see it's running currently. You can see the code for it. There's logs that get created here. You can see the logs of when the job is finished, and so on. Now, I realize I'm running out of time. Let's try and answer some of these questions. Yeah, how do you keep data versions and model versions and feature versions for various experiments in sync? Okay, so this is unrelated, but because we've looked at the basic idea of Airflow pipelines, let's have a look at models briefly in our platform. So I hope I have a model in here. This is a different project, and I do have one model here. We can see it's called MNIST. So what we can do, so we've trained the model. I probably have an experiment related to it. This is the experiment for the model. And in this case, I didn't train it using a training data set, but if we did train a training data set, I would have a link to it here, and I could look at the training data set in the feature store, and I'd be able to then track between them. So what we can do is we started our model. We can look at the model. We have some, you can return a dict with these metrics that appear here in the UI. And from here, you can navigate back to the experiment that was used to train the model. And the experiment has a copy of the program, a copy of the conda environment. And then if we have a link to the train data set, we'll have that there. We have the logs for it. So basically, we have this provenance. And this is all available via APIs as well, not just via the UI. Another question, how do you compare Hopsworks to Azure ML? So Azure ML is Python only. This is Python and Spark. Both have GPUs. Look, we have a lot of customers who use Azure ML and they're happy with it, but they need a feature store, so they use our feature store. So I won't say we're competing with anyone. Now I'd probably run out of time so what I'll do is I'll just show you. I did actually create that Airflow job earlier here, but I think I might have deleted this. Yeah, so you would basically create the second Airflow. So we can just look at this job that ran. So it's still running, actually. It's going to run for quite a bit. But eventually we'll write our feature group to the feature store. It's written it, but it hasn't probably finished writing it to the online feature store yet. So that's basically it, because I realize we're out of time. So you can go ahead and I'll leave it as an exercise to the reader to create more jobs using notebooks, and then we can create more Airflow programs. But you'll get a feel for, there's a lot more capabilities. We haven't gone into the details of Airflow and how it works, but I'll leave that as an exercise to the reader for how to figure out a lot of that. So I think I've gotten most of the questions here. Unless anyone has any more, I'll take one more, but we're a minute over time and I don't want to eat into people's time. Anything in the chat here? Okay, so yeah, Hopsworks available on premise. There's a question on that. Okay, then, I mean, I think, Natalia, I think we're done for today.
Yes, really great presentation, Jim. Great turnout and very engaging questions. Thanks everyone who attended. We'll be sending the slides and the video by email. And if you have any questions or if you want to have a demo of Hopsworks, please reach out to us. And I hope you have a good evening or a good day, depending where you are. Thanks, Jim.
Thanks, everyone. All the best. See you now. Bye-bye.